Hello, everyone. This is Yiding Feng. I'm a fifth-year PhD student from Northwestern Computer Science. My research interests including online algorithm and mechanism design.
Today, I would be happy to talk about my joint work with Red from Chicago and Amin from Stanford. The title of this paper is Two-Stage Matching and Pricing with Applications to Ride-Hailing. As you may infer from its title, this paper is motivated by the recent applications in the ride-hailing. It has been reported that recently some of the ride-hailing platforms has modified their matching strategy. Previously, once a trip request from a rider arrived at the platform, the platform needs to respond to that request immediately. However, in order to improve the matching efficiency, the ride-hailing platform introduced some latency to respond to those requests, and therefore it enables them to batch the trip request in a short time period and then make the matching decision for all those requests together. In this paper, we study a theoretical model inspired by this new paradigm and try to identify matching algorithms with good efficiency guarantee. First, let's introduce our model, and for simplicity, we will use the language of ride-hailing application. So suppose we are given a bipolar graph. One side of the node corresponds to the rider, and another side of the node corresponds to a driver. And the edge between them denotes if we can match a rider to a driver. And let's first consider the driver side. For each of the driver, we will assume that it will be associated with a different weight. And in our two-stage problem, the rider will be partitioned into two sets, RA and RP. And for every rider in RA, it needs to be matched immediately. And for every rider in RP, it will be associated with a probability. And we will specify this probability next. So the two-stage matching process will be defined as follows. So at the beginning, the matching algorithm will observe the whole bipolar graph, as well as the weight and the probability pi for every rider in RP. So in the first stage, the platform needs to pick a matching M1 between the rider in RA and the driver set D. And then in the second stage, the nature will sample a subset RP tilde from RP as follows. So every rider I in RP, it will be accepted. In other words, will be added into RP tilde with its own probability pi independently. And once RP tilde has been realized, the matching algorithm will need to pick a matching M2 between RP tilde and the driver which are left unmatched from M1. And our goal is to maximize the expected efficiency, in other words, the total weight of the matched driver. And here, the expectation is take over the randomness of both the matching algorithm and the nature. In other words, the realization of RP tilde. In order to have a better understanding of the model, let's look at the instance on the right-hand side. Now, first, in the first stage, the matching algorithm needs to pick a matching between RA and D. And suppose that it will match the first and the third rider. And the second rider will just leave. And then we will move to the second stage. First, the nature will realize RP tilde, which is a subset of RP. Now let's suppose that the fifth rider will be added into RP tilde. And the driver will be matched to him is the fifth driver. Cool. And now we have a matching which match the first, the third, and fifth driver. And the total weight is 9. This work is closely related to the online bipartite matching literature, where people consider multiple stages instead of just two stages. However, each stage will only consider a single rider. And as we mentioned at the beginning of this talk, comparing to this classic model, our new model captures this new paradigm where the ride-hailing platform tries to accumulate the trip request and makes a decision in batches. And it has been reported that in practice, there is a significant efficiency improvement by doing so. And another line of related work is a two-stage stochastic matching, where different stochastic process and objective has been considered. Very recently, Red and I have a follow-up work considered a k-stage fractional matching with batch arrival. So comparing to this current model, we consider k-stage instead of just 2-stage. And once again, every stage can contain multiple riders. However, instead of requiring to output an integral solution, in this follow-up work, we will only consider the fractional matching. In this paper, we will evaluate the performance of the matching algorithm using a standard measure of the competitive ratio. Specifically, we will fix a benchmark opt, and we will define a competitive ratio of the algorithm alg versus this benchmark opt as the worst ratio over all possible instances, where the ratio is between the performance of the alg on this instance versus the performance of opt on this instance. And in this paper, we will consider the following two benchmarks. The first one is optimal offline. Specifically, we will consider a policy which will know the exact realization of RP tilde, and it will pick the maximum weighted matching between RA union RP tilde and D. Also, we will consider a weaker benchmark, which is optimal online. It can be easily observed that once we fix the matching in the first stage, in the second stage, it is optimal to find the maximum weighted matching between the RP tilde and all the drivers which have been left unmatched in the second stage. And therefore, the optimal online is basically an algorithm which will search over all possible matching M1 and try to pick the one which will maximize its expected efficiency. And in the later of this talk, we will show that this optimal online is not polynomial time computable. Cool. Now it is ready for us to present our main results. In this paper, we basically consider a two-stage matching, and we try to identify the competitive ratio against both optimal offline and optimal online. And using the algorithm in the literature of online bipartite matching and other two-stage stochastic matching model, we can get some algorithm who introduce the competitive ratio of 2/3 for the case where all the driver has equal weight, and 1 minus 1 over E when all the driver has different weight. And in our paper, when we consider a competitive ratio against optimal offline, we obtain a tight bound of 3/4. And we'll further show that if we are switching our competitive ratio against optimal online, so we can get slightly better bound for both the unweighted driver case and the weighted driver case. And we also show that the optimal online is F pitas hard. And of course, all our lower bound, basically the algorithm which will achieve those competitive ratio, is the polynomial time algorithm. In the remaining time of this talk, we will talk about the following three parts. First, we will talk about our first algorithm hedge, which will attain the optimal 3/4 competitive ratio against the optimal offline. And it will be used as a building blocks for the further improved competitive ratio against optimal online. And next, we will characterize the optimal online and try to argue that it will be F pitas hard, and it will have a connection to the submodular maximization. And at the end, so we will present our second algorithm, which we call hedge and greedy. It will achieve a slightly better competitive ratio if we are switching the benchmark from optimal offline to optimal online. And this algorithm is basically a combination of the hedge, which we described in the first part, and the greedy algorithm for the submodular maximization. Now let's talk about our first algorithm hedge, which is a 3/4 competitive against the optimal offline. And for simplicity, we will first focus on the setting of unweighted drivers. In other words, all the drivers will have an equal weight, and our objective will be maximize the size of the matching produced by the algorithm. And let me first introduce some intuition behind this algorithm. To understand this intuition, let's consider the following thought experiment. where we will, instead of assuming that the second stage with RP tilde is generated by a stochastic process, instead we will assume that it will be picked by an adversary, which is unknown to the matching algorithm. And because in this case, there's no information about the second stage for our algorithm. So how should the platform or the algorithm pick the matching in the first stage? Well, if the first stage graph is a complete bipolar graph, then our algorithm should output a matching M1 uniformly at random, such that each driver will be matched with equal probability. In other words, we want to match the drivers in the first stage as uniform as possible, because we have no information about the second stage. And basically, then the question is, how could we generalize this to if the first stage bipolar graph is not complete? And to do this, we will introduce the following structure on the graph, which we call the demand balance decomposition, DB decomposition. And specifically, we will partition the vertices in the first stage, RA and D, into several pairs, which satisfy the following properties. First, for each pair, we can define the demand per driver, which equals to the ratio between the number of riders over the number of drivers in this pair. And without loss of generality, we can index those pairs such that their demand per driver is weakly increasing. Now we will require that we will satisfy the following two uniformity property. The first uniformity property 1 will require that for each pair, there will exist a random matching within this pair such that every driver will be matched with equal probability equals to dk. And the second uniformity property will require that there doesn't exist edge from a rider in the high demand pair to a driver in a low demand pair. And let me put a remark here. Suppose that our first stage bipolar graph is a complete bipolar graph. Then this DB decomposition will leave the whole bipolar graph as a single pair. And basically, we will match every driver as uniform with equal probability. Cool. Now, in order for us to have a better understanding of this DB decomposition, let's once again run an example on the right-hand side. Now we have a bipolar graph. Now let me remind you that this bipolar graph corresponds to RA and D. First, we can consider the following partition containing two pairs. We can compute their corresponding demand per drivers, which is equal to 1/2 and 3/4. And it can be observed that this partition doesn't satisfy our demand balance decomposition because it will violate the uniformity 1. Because for the second pair, we cannot match every driver with probability equals to 3/4. And now we can consider another partition, which partitions the graph into 3 pairs. And once again, we can compute the demand of each pair. And it turns out that this partition also does not satisfy our requirement because it violated uniformity 2. Because you can observe that there is an edge from the rider in pair 3, which has demand equals to 1, to a driver in the pair 1, which has the demand of 1/3. And at the end, so we can consider this partition, which contains 3 pairs, and it will satisfy all our property of the demand balance decomposition. Once we have this understanding of the definition of DB decomposition, one of the follow-up questions is, how could we show its existence? And it turns out that we can show its existence as well as how to efficiently compute it by introducing the following convex program. so we will have the constraint correspond to the matching constraint, and the objective function will include the function f, which could be an arbitrary differentiable, monotone increasing, and strictly convex function. And let me remind you that if we're trying to pick the proper capital F, so this objective function, it will be equivalent to the Rosen social welfare or the Nash social welfare. Basically, it's trying to introduce some of the fairness of all the drivers we want to match in the first stage. And now we can have the following technical lemma of this DB decomposition. Specifically, we can assume that X star be the solution of this convex program. And then we can define a subgraph of this bipartite graph, where we will consider only the edges where their Xij star is positive. And we will define all the pairs in this partition to be the kinetic component. And then this technical lemma will suggest that this partition will form a DB decomposition. And moreover, so this Xi star will be the probability induced by the random matching, which satisfies uniformity 1. In other words, for each pair in this partition, we can match every drivers in this pair with the equal probability, and it will correspond to Xij star. And this lemma can be proved by using the KKT condition of the convex program. Once we have introduced our DB decomposition at its technical lemma, it is ready for us to present our hedge algorithm, which is a 3/4 competitive against the optimal offline. And this is the optimal competitive ratio we can get against the optimal offline. And it will work as follows. First, we will solve X star from the convex program. And then we will compute a matching distribution such as its edge probability will correspond to X star. Then in the first stage, we will randomly generate a matching M1 under this distribution. And in the second stage, we just return the maximum matching M2 between RP tilde and unmatched driver in D. And let me remind you that here we are only considering a case where all the driver has an equal weight. First, let me put some remark here. First, due to the integrality of the bipartite matching polytope, our step 2 in the hedge algorithm is well defined and polynomial time computable. Second, it can be observed that our hedge algorithm do not use any information about RP in the first stage. In other words, it will attain 3/4 competitive even if we are in an adversarial environment. And third, so to show this optimal competitive ratio of 3/4, we will use the standard primal-dual analysis, and we will construct the dual solution using our DB decomposition structure. Before we finish this part, let me add a few sentences about this DB decomposition. So far, we have introduced it for the case where all the driver has equal weight. And when we move to the case where all the driver can have a heterogeneous weight, basically we need to modify our convex program by modifying our objective function in the convex programming using a weighted version. And the corresponding definition of the DB decomposition, in other words, its property need to be satisfied, need to be modified. And please check our paper for more technical detail. And for the unweighted case, our DB decomposition is almost equivalent to the so-called matching skeleton introduced in the literature. And this matching skeleton itself is a special case of the Edmond skylight decomposition on the bipartite graph. And this matching skeleton technique has also been applied for other two-stage matching models. And in this sense, in this paper, our DB decomposition generalizes this matching skeleton to the vertex-weighted case.
So far, we have presented our first algorithm hedge, which attains the optimal 3/4 competitive ratio against the optimal offline. And now we will shift our attention to the optimal online. We will argue that it will be f p times hard to compute the optimal online and its connection to the submodular maximization. Now let's talk about the complexity of computing the optimal online. And to do this, let's first introduce the following two set function. Let's say for an arbitrary set of driver S, we'll define rho 1S to be the maximum weighted matching between RA and S, and rho 2S to be the expected maximum weight matching between RP tilde and S, and the expectation is taking over RP tilde. And let me remind you that both rho 1 and rho 2 can be shown that they are both monotone submodular function. First, as we mentioned before, the optimal online policy basically needs to solve the following question. It needs to partition the driver set into S and D minus S. And basically, we will try to find the max weight matching between RA and D minus S, and the max weighted matching between RP tilde and S. And here comes another observation. It suggests as follows. The optimal online policy will pick the matching M1 star in the first stage, where M1 star is a maximum unweighted matching. And this observation is easy to say its correctness for unweighted setting when driver has equal weight. But we want to emphasize that this observation too will also hold even when drivers has heterogeneous weight. And due to this observation too, we can rewrite the optimization program, the optimal online policy to solve. And previously, the optimal online policy need to consider all possible partition, need to consider all subsets of driver S. But now we can restrict our attention to all subset S within B. And the set B is defined as follows. So we will say a subset S is in B if and only if all the drivers in D minus S can be fully matched by a maximum unweighted matching between RA and D. And because of this definition, rho 1 D minus S will be equals to the summation of all the weight of the driver in D and D minus S. And for someone who are familiar with the mature theory, so this set B is actually the set of all bases of dual transversal mature corresponding to the bipolar graph RA and D. Cool. So at this point, we know that the optimal online policy basically needs to solve the following set function optimization and subject to a mature feasibility constraint. And so you may notice that in set function optimization, we need to have a value query to rho 2. And it turns out that by doing a sampling, we can access the epsilon closed value queries of rho 2 in polytime. And the follow-up question is that, can we use those epsilon value queries to obtain a near optimal approximation for the optimal online policy in polytime? And in this paper, we show that the answer is no. In other words, computing the optimal online policy admits no FP task unless P equals to NP. And the proof is basically a reduction from max K cover problem. Now we have discussed the FP task hardness of the optimal online. Next, we will present our second algorithm, which is a polytime algorithm, and get an improved competitive ratio against the optimal online. Our second algorithm, hedge and grade, which attains an improved competitive ratio against optimal online, also use our previous characterization of the optimal online policy. Specifically, the optimal online policy solves the following set function optimization. And let me point out that the objective of this optimization is the sum of linear function and non-negative monotone submodular function. And it has been studied in the literature that there exists a greedy style algorithm for maximizing the sum of linear function and non-negative monotone submodular function. And with this greedy style algorithm in hand, we are able to present our second algorithm, hedge and grade. It will be parameterized by a parameter lambda between 0 and 1. So in the first stage, this algorithm will run hedge with probability lambda and run this greedy style algorithm with otherwise. And in the second stage, it will just return the maximum weighted matching between RP tilde and the remaining driver. And basically, in our paper, we show that by choosing the proper lambda, we will achieve a competitive ratio against optimal online, which is slightly better than 3/4. And let me remind you that this theorem basically suggests that the worst instance for the greatest algorithm and the worst instance for the hedge algorithm does not match with each other. And therefore, by running a mixing of them, we can improve our competitive ratio. And in practice, instead of running both two algorithms with a fixed probability, we can use sampling and the Monte Carlo method to estimate the performance of those two algorithms and run the beta of those two. And the proof of this theorem is a little bit complicated. So in a high level, we try to identify the worst instance by a factor revealing program. And this is a nonlinear program whose optimal solution is the lower bound of the competitive ratio of hedge and break against the optimal online. And you can check out paper for more detail of this part. Here are the main results of this paper. This is the end of my talk. If you have any question or comments for my talk or our paper, please feel free to contact me through my email. Thanks for your listening.